Okay, let's start. Welcome everybody. Okay, it's good morning or good evening, depending on which part of the world you are in currently. Okay, well, great. We are happy to have Brian. Okay, he's gonna talk about rational curves and Delpezo surface in positive characteristic. Okay, I'm looking forward to this talk. Okay, go ahead.
Great. So thank you very much for the invitation to speak. It's nice to be here. Let me share my screen and hide the library. So thanks again. So as Om said, my title is Rational Curves on Delpezo Surfaces and Characteristic P. And any new work that I talk about today will be joined with Roya Beheshti and Eric Riedel and Sho Tanimoto. All right. So here's the setup. Let's suppose that X is a smooth faunal variety over a field K. The guiding question that we'd like to consider is the following. Can we classify, let me say, the irreducible components of the parameter space, or let me say maybe the moduli space of rational curves on X. Okay, so following Mori's work, we know that we can expect X to carry a lot of rational curves. And then the question is, what are they? Can we classify the components of this moduli space? This is some kind of classification result. And people have understood for a long time that understanding the rational curves on a faunal variety is a good way to get a handle on its geometry. So this is a well-known question. It's been studied for a long time. It turns out it doesn't matter so much what sort of type of moduli space you use. So I'm going to use the following. By rat X, sorry, let me see if I can move this out of the way. Good. So by rat of X, I'm going to mean the union of the irreducible components of the Kontsevich moduli space of stable maps, which generically parameterize rational curves. So I don't want to allow the strange components which parameterize only reducible curves. I'd like my components to generically parameterize irreducible curves. And the reason we work in this space is because we want to allow our curves to break. Okay. So this is our question. Can we classify the irreducible components? Over C, there's lots and lots of examples of faunal varieties for which this question has been studied. So let me mention a few. One of the most famous is the case of hypersurfaces. For faunal hypersurfaces, we have a pretty good understanding of the spaces of rational curves on them, although it's not totally complete. So one of the first papers in this direction is due to Harris, Roth, and Starr. Then later on, there was work by Beheshti and Kumar, Riedel and Yang, which settle the situation for general faunal hypersurfaces of almost any degree. More recently, there's been some interesting work by Browning and Vische and Browning and Sawin considering arbitrary smooth hypersurfaces of very small degree compared to their dimension. In any case, hypersurfaces is one class of varieties where we know a lot about rational curves. Another is torque varieties. So here I've written Bourqui's name. Bourqui's done a lot more. He studied various flavors of moduli spaces of curves on torque varieties, but in particular, you can sort of understand rational curves based on his results. Another maybe class worth mentioning is the space of homogeneous varieties, of the type G over P. So these were studied by Thompson and then by Kim and Pandre Panda. And there's lots more. Maybe some people here have also proved results, which is great. There's a ton of results out there. I just wanted to give a short list of some, maybe some of the more famous cases. Then another option, which has a little bit of a different field, is to work over a finite field. So if we're working over a finite field, then we can actually count rational curves. So by this, for example, we can look at the moduli space, and then we can count FP points on each component. And this will be counting, rational curves of sort of each, the rational curves parameterized by each component of the moduli space. And if we do this, this leads to a version of Madden's conjecture. So this is maybe a special case of the function field version of Madden's conjecture. Okay, so it has a little bit of a different field. So in general, you might ask, well, okay, so how should we expect these components of the moduli space to behave? How should we understand them? So I wanted to advertise this sort of guiding principle, which is known as geometric Madden's conjecture. It's combining ideas of a few different people. So the first part of this principle regards pathological families of rational curves. So we predict that pathological families of rational curves are controlled by the Fujita invariant. So there's a couple things to say here. First, what do we mean by pathological? It's just a principle. We don't need to be precise. But the types of things that, the types of pathologies we might want to consider would be, for example, families which have larger than the expected dimension, or maybe families which fail to be free. Or other options. That's not a complete list, but it's families which are unusual in some way. And then the hope is that these are controlled by the Fujita invariant. So I'm going to define this in a second. But for now, I just wanted to mention, what is it? So the idea is that it's some measurement of the negativity of the canonical divisor. So it's an invariant coming from the minimal model program. The idea is that the pathologies of rational curves are somehow controlled by the curvature of the canonical divisor. Okay, that's the first part. The second part of the conjecture says that after we remove the pathological families, the families that are left stabilize in some sense. So they admit some sort of systematic behavior as the degree gets large. Here's a couple examples of what that might mean. So for example, we might expect that once we remove the pathological families, maybe we just have a unique component of the moduli space of rational curves representing any given algebraic equivalence class. Certainly that's a phenomenon that's quite common, and maybe we can hope for it in general. More generally, if you remember, so Madden's conjecture is all about counting rational points on these moduli spaces, and that's a motivic type of calculation. So sort of by analogy, if we want to work over a different field, maybe we can ask that the components of the moduli space have some type of homological stability or some type of motivic stability. Again, as the degree increases, there should be some sort of motivic or homological properties which are preserved as the degree goes up. So together, these are called geometric Manning's conjecture. And in particular, this gives us a classification, sort of an approach to our classification problem, right? It has two parts. First, if we use the Fujita invariant, we can classify the pathological families. And then afterwards, maybe we're hoping for some kind of uniqueness. So together, these two predictions would tell us about all the components of rational curves on our faunal variety. Okay. So now let me define the Fujita invariant before we get any further, just to sort of fill in that gap. So suppose that X is a smooth projective variety. In practice, we'll imagine that X is maybe fano or uniruled. And let L be a Neff-Q Cartier divisor. So Neff in the sense that it has positive non-negative intersection against all curves. If L is big enough, then we define the Fujita invariant in the following way. We'll denote it by A of XL. This is the notation that's used in Manning's conjecture. And it's defined to be the infimum over all real numbers T, such that Kx plus T times L is pseudo-effective. Okay. So how should we be thinking about this? Well, this is some measurement of how negative the canonical divisor is when compared against the big and Neff divisor L. So here's a picture of what's going on. So if L is a big divisor, then that means in particular that L is going to be lying in the interior of the pseudo-effective cone. So this is supposed to be a picture of the pseudo-effective cone divisors. L is lying in the interior. On the other hand, if we have a uniruled variety, then maybe Kx should be on the exterior of the cone. And what this invariant is measuring is how much of L do we need to add on until we hit the boundary. So again, it's measuring the negativity of the canonical divisor against L. There's a couple other cases that we need to define just for the sake of completeness. So if L is a Neff divisor which is not big, then we define the Fujita invariant to be infinity. This might look a little bit weird. We don't really want to use the same definition. We should view this as sort of an exceptional case. So we just formally set it to be infinity. Finally, if X is singular, and if we assume that it admits a resolution of singularities, we define the Fujita invariant to be the Fujita invariant of the pullback of L to the resolution.
Hi, Brian, quick question.
Yeah.
This singular case, I mean, wouldn't it be a problematic unless the X has a terminal or let's say canonical singularities, like showing the independence of the resolution, this invariant?
That's a great question. So I think almost noting that if X has worse than canonical singularities, this definition is going to be different than this definition. And that's absolutely, right. I want to define it to be a birational invariant. So that's sort of the point implicitly here is that for smooth varieties, this is a birational invariant. And for singular varieties, I'm going to force it to be birationally invariant by pulling.
And it is going to be independent of the resolution? That's right.
Due to the birational invariance, it's going to be independent of the resolution. Yeah.
I see. Okay.
I mean, the nice thing is that this definition works for arbitrarily singular things. So it just allows us, allows us to handle them all at once. Although you're right that it's an MP way of thinking about these pseudo-effective thresholds.
Okay.
Sorry. So maybe the first example is, suppose that X is Fano, and suppose that we're polarizing it with the anti-canonical divisor. Well, then the Fujita invariant's equal to 1, right? So I think this is pretty clear. If you take the canonical divisor and you're asking how much of the anti-canonical do I need to add on to cancel it out, the coefficient's going to be 1. So this is sort of a basic example. More generally, how should you be thinking of the A invariant? Well, the A invariant, you can kind of think of it as like a birational version of the index of a Fano variety. So, if X is Fano and H is proportional to the canonical, then we're just getting the index. And due to the birational invariance, it's some birational version of the index. So just as an illustration of this idea, here's a particular example. I guess maybe I should say this is in characteristic 0. It's probably true in characteristic P, but just to be safe, let me say characteristic 0. So suppose that X is smooth projective, and then suppose that we're polarizing it by a big enough Cartier divisor. So we should say big enough Cartier divisor. Then the Fujita invariant is larger than the dimension of X if and only if XL is birationally equivalent to projective space equipped with the hyperplane class. So we have a similar theorem for the index, right? The only possible index which is larger than the dimension is the dimension plus 1, and that only happens for Fano varieties. This statement is saying that a similar type of classification happens for the Fujita invariant. So if the Fujita invariant is larger than the dimension of X, then basically projective space is the only example, up to birational equivalence. So this is sort of getting at a general phenomenon. The larger the Fujita invariant is, the more special your variety is, just like for the index. So for, when the Fujita invariant is very large, you can do some sort of classification. In general, this principle sort of helps us to understand what it means. Okay. So now that we've defined the Fujita invariant, now we can return to our sort of guiding principle. So let me sort of state it again. This is a discussion of pathological families of rational curves. So let X be a smooth projective Fano variety. And suppose that M is an irreducible component of the moduli space of rational curves. And suppose that it parametrizes pathological curves in some sense. Again, we haven't really made this precise. Then we can expect that the curves factor through a generically finite morphism, F from Y to X, such that the A invariant, the Fujita invariant of Y with respect to the pullback of the canonical divisor is strictly larger than the Fujita invariant of X with respect to minus kx. This is of course just a fancy way of writing. Okay, so what does this say? So this is saying that families of pathological curves, maybe we should expect that they come from sort of the subvarieties or the maps where the canonical divisor is somehow more negative than the canonical divisor for X. It's a sensible idea. It seems like maybe it's something worth trying. To be fair, what this principle looks like will depend upon what you mean, what you mean by pathological. So sometimes, depending upon precisely what you mean, you might want to allow maps where the A invariance equal as well. you wouldn't want to allow arbitrary maps, but maybe some of the maps where equality is attained should also be considered in this principle. Okay, so here's an example of this principle at work. This is a result due to Sho Tanimoto and myself. So suppose that X is a smooth Fano variety and that we're working in characteristic 0. And also let's suppose that the curves parameterized by some irreducible component M, they don't form a dominant family. So they sweep out a closed subvariety of X. Then it turns out that the Fujita invariant of this subvariety with respect to this restriction, the restriction of the anticanonical, is strictly larger than the Fujita invariant of X. Okay, so this is exactly verifying this principle where our pathology is non-free, right? So here these are exactly the components which don't parameterize any free curves. And the idea is then that the corresponding family of curves has to factor through some subvariety, satisfying this inequality on the curvature of the canonical divisor. So let me add as a remark, in fact, it turns out there exists a closed subvariety, V, properly contained in X, which contains all such subvarieties Y. So this is a result of Haken and Jiang. And in practice, we can use techniques from the minimal model program to try to understand what does this closed sublocus look like. It's usually easier to find these subvarieties than it is to just understand rational curves by hand somehow. So this gives us a different way where we can use tools as a minimal model program to try to approach this classification problem for rational curves. Again, maybe I should add on this remark, where is this coming from? Ultimately, this is coming from Birker's work on the boundedness of mildly singular phonos. Following Birker's work, we actually know a lot about the Fujita invariant in characteristic 0. There's some sort of boundedness statement coming from what Birker proved, which allows us to give some very strong structural theorems for the Fujita invariant. Okay. So thus far, I've been trying to give sort of a general picture of the area of classification of rational curves. I'd like to turn now to Delpezo surfaces. So from now on, we're going to be working over an algebraically closed field. And we'd like to specialize our questions to this particular scenario. Okay, so let me start with a couple quick reminders. A Delpezo surface, or respectively a weak Delpezo surface, is a smooth projective surface S over a ground field such that minus Ks is ample, or respectively big enough. And we have a pretty explicit description of what these look like, and the description's the same in any characteristic. Aside from P1 cross P1, they're all blowups of P2 in at most 8 points, where precisely the 8 points need to be in general position in some sense. Depending upon whether you want a Delpezo or a weak Delpezo, general has slightly different meanings. In any case, they're almost all blowups of P2. Then the degree of a weak Delpezo surface, I'm going to denote the degree by D, usually. And it's just the square of the anticanonical. So for example, P2 has degree 9. And each time you blow up a point, the degree drops by 1. So in particular, when we have low degree, that means that we've blown up lots of points. And the Delpezo surfaces of low degree are much more complicated than the Delpezo surfaces of high degree. So we're interested in studying rational curves. And rational curves, if we're working over a field of characteristic 0, the behavior of rational curves on Delpezo surfaces was analyzed by Testa. This is a theorem due to Testa, except that Testa proved this theorem for almost all Delpezos. So he proved it for Delpezos of degree at least 2, and then also for general Delpezos of degree 1. And then in the paper that I'm talking about, we handle the last case just to finish off this theorem of arbitrary Delpezos of degree 1. So here's the statement. This is how rational curves look like on a Delpezo. So let S be a Delpezo surface, and let M be a component of the moduli space of rational curves, which has anti-canonical degree at least 3. Then M has one of the 3 following types. So the first possibility is that M generically parametrizes by rational maps. By rational maps onto free curves. So maybe we should think of this component as like the good component. Parametrizing by rational maps onto free curves, that's a nice property for a component to have. Another possibility is that M parametrizes multiple covers of a rational curve C such that minus ks dot C is equal to 2. So for example, if our Delpezo surface admits a conic fibration, then it's possible for M to parameterize multiple covers of the fibers of this map. The last possibility is that M generically parametrizes multiple covers of a rational curve C such that minus ks dot C is equal to 1. So these will be, either -1 curves, or if S has degree 1, then they can be the singular elements of the anti-canonical linear series. And these are the 3 possibilities. So furthermore, not only can we say, what types of curves does M parameterize, but it's also true that almost every Neff curve class is represented by exactly one family of free curves. So this is this irreducibility idea that we've mentioned briefly before. Most of the time, we expect there just to be a unique component representing a given numerical class. And there's a couple exceptions coming from multiples of the anti-canonical linear series. But basically, this is always true. Okay, so this is a great theorem. It's a nice explicit statement about what happens for Delpezo surfaces. It's basically a complete classification. So maybe let me add as a remark, let's just think about how this fits into the framework of geometric Mannen's conjecture. So first of all, suppose that we have a rational curve in our Delpezo surface, and suppose that minus ks dot C is equal to 1. Then the A invariant, the Fujita invariant of C is going to be equal to 2. Right, so on P1, the canonical divisor is O of -2, which means we need to add on twice this divisor to get back to 0. So if we have a curve satisfying this, this intersection condition, then these will be exactly the curves with larger A invariant than S. And similarly, if minus ks dot C is equal to 2, then the Fujita invariant of C is equal to 1. which is equal to the A invariant of S. And finally, one can show that there's no sort of interesting maps with larger A invariant, sort of aside from these two examples. Like these are somehow an exhaustive list of the interesting features of the Fujita invariant for the Delpezo surface. So then, according to geometrics-Mannon's conjecture, again, maybe depending on how exactly we're phrasing it, this sort of predicts the existence of these exceptional components, right? So we have two types of exceptional components. One of them sort of factors through a conic, and one of them factors through like a minus KS line, and that's exactly what the Fujita calculation is confirming for us. Okay, so this is this is an example of geometric-Mannon's conjecture at work. So the main question that I'd like to consider is what happens in characteristic P? So first of all, can we classify the components of the moduli space of rational curves for a Delpezo surface S? In particular, maybe it has a similar description. And the second question is, does the Fujita invariant still control the pathological components? So in characteristic P, we know much less about the Fujita invariant because our knowledge of it depends on the minimal model program. So, here's how you should be thinking about this question. Here's what it means. So in characteristic P, we find new pathological families. For example, there are dominant inseparable families of rational curves. And maybe we can think of this as a type of pathology for a family of rational curves. And so it's something we'd like to get our hands on. We'd like to be able to say, when does it happen? On the other hand, we also have new examples of maps which can have larger Fujita invariant. So dominant inseparable maps, like purely inseparable covers, can sometimes increase the Fujita invariant. So we get these sort of new examples in characteristic P. And the question is, do these two phenomena match up? Can we explain the presence of dominant families of inseparable curves using the Fujita invariant in the same way? So maybe just to summarize, so here's what I'm going to be doing in the remainder of the time we have. So first, we'd like to classify characteristic P pathologies. And I'm going to focus on two. So the first type of pathology is when we have a dominant family of rational curves, which has too large dimension. This can only happen in characteristic P. In characteristic 0, if you have a dominant family of rational curves, the general one is free. And so the family has the expected dimension. But in characteristic P, if you have an inseparable family, that doesn't need to be true. And then we'd also like to get some handle on the dominant non-separable families of rational curves, sort of as we talked about before. And the hope is that both of these pathologies are controlled by properties of the canonical divisor. And then once we've handled these pathologies, maybe we'd like to also classify components. I'm not going to do this for every Delpezo surface, but maybe for most Delpezo surfaces, we can classify the components of the parameter space of curves. Okay. So the first step is to study dominant families of rational curves on Delpezo surfaces which have too large dimension. So let me give a couple examples of this construction. Maybe the first example to keep in mind is, suppose that we fix a pencil of singular cubic curves in P2. So these are the so-called quasi-elliptic pencils. And they can only happen in characteristics 2 or 3. So suppose we fix a quasi-elliptic pencil, and then suppose we blow up 8 of the base points. So not all 9, but we blow up 8 of them. The result, it turns out, if you at least in some situations, is going to be a weak Delpezo of degree 1 such that every element in the anti-canonical linear series is singular. Right? The curves in the anti-canonical linear series are going to be the strict transforms of this singular pencil. So what this means is that we're going to get this family is a family of rational curves which has two large dimensions. Each of these singular cubics is of course a rational curve, and if because it's a weak Delpezo of degree 1, the expected dimension of something with anti-canonical degree 1 should be a 0-dimensional family. But here we have a 1-dimensional family. So we get a dominant family, which has two large dimensions. Okay, here's another similar example. So I think this example was first considered by Keel and McKernan, and many other authors have considered it since. It's a good example of a pathological weak Delpezo surface. It's pathological in many different ways, and here's one of them. So suppose that we're working in characteristic 2, and suppose we blow up all 7 F2 points of P2 and then base change to the algebraic closure. So based on the incidence correspondences between these points, and sort of understanding the lines and conics on them, the result of this blow up is going to be a weak Delpezo surface of degree 2. And one of the interesting pathologies of this surface is that if you look at the anti-canonical linear series, it defines a purely inseparable map. So just like for any weak Delpezo surface of degree 2, the anti-canonical linear series defines a map to P2 of degree 2, which is generically finite. And for this particular surface, it just happens to be purely inseparable as well. So because of that, we obtain a Frobenius factoring. So let me explain what I mean. So the function field of S, it's obtained by adjoining some square root of an element in the function field of P2, which means that if we look at the geometric Frobenius, it's going to factor rationally through S, right? So the function field is an extension of the function field of S. So we get a diagram like this, where this is a rational map. Let me maybe call it F. So here, one of the, from the perspective of rational curves, what's interesting about this example? Well, it turns out if we take a component of the moduli space of rational curves on P2, and then take its F image, just sort of, if you consider the curves avoiding the locus where this map's not defined, then we'll get a component of the parameter space of rational curves on S, which has two large dimensions. So, the curves on P2 define parameters, define components on S with two large dimensions. And why is this so? Well, this is closely related to this Fujita invariant calculation. It turns out that the Fujita invariant of P2 with respect to the pullback of the minus Ks is strictly larger than the Fujita invariant of S. I'm abusing notation slightly here. Like, really, we should resolve this to be a morphism, and then this would be true. Okay, so this is this is another example of our sort of main principle of work. Okay, so now let me state the first theorem. Suppose that S is a weak Delpezo surface, then the following conditions are equivalent. So the first statement is that S admits a dominant family of rational curves with two large dimensions. Okay, this is a pathology we're interested in. The second condition, the second equivalent condition, is that every member of the anti-canonical linear series of S is singular. Okay, so we get some, sort of strange behavior of this linear series. The third condition is now sort of hearkening back to our work on the Fujita invariant. It says that there exists a generically finite dominant morphism F such that the Fujita invariant of Y with respect to the pullback of the canonical divisor is strictly larger than the Fujita invariant of our surface S. So we can view this as a confirmation of the principles of geometric Manin's conjecture for weak Delpezo surfaces. This pathology is controlled in some sense by this Fujita invariant comparison. Okay. So let me remark, the surfaces satisfying condition 2 are classified by Kawakami and Nagawaka. Kawakami and Nagawaka were interested in studying different types of pathologies for weak Delpezo surfaces. And in the course of their study, they actually classified surfaces satisfying this condition. It turns out that there's 3 infinite families alongside 11 sporadic examples. So we have sort of a complete list of the surfaces of this type. They only occur in characteristic 2 or 3, and they only occur when the degree is 1 or 2. So these pathologies are kind of special in that they can only sort of occur in a very limited range. Okay, so I wanted to give an idea of the proof, just to quickly sort of overview what is, how would you maybe hope to prove this. So here's the setup. Suppose that M is a so first let's prove that 1 implies 2. So here we have a family of 2 large dimension, and we want to show this second condition on the anti-canonical divisor. So suppose that M is a component of the moduli space parametrizing a family of rational curves, which is dominant and has 2 large dimension. We'll call that dimension R. So the idea is we're going to fix R-1 general points in our surface. And then we're going to consider the 1-dimensional subfamily of M parametrizing curves through these points. So because we're considering a 1-parameter family of curves where we're fixing a bunch of points, by bend and break, that means that B has to parameterize some broken curves. So, the generic curve parameterized by B will be irreducible, but some special curves will be broken into reducible components. And the key idea, maybe that makes this proof work, is that the broken curve is somehow constrained by the fact that it goes through the general points. So how can you think about this? Well, when you run bend and break, you have very little control over the broken curves that result. But this construction allows us to have more control. You can't have too many sort of random components spouting off, because then you wouldn't have, if you have like a lot of extra components, you wouldn't have enough positivity for the remaining components to go through all these R-1 general points. So that's the key idea. Somehow the bend and break is constrained by this construction. So using this idea, you can prove that, in fact, by induction, if you have such a family of large dimension, then you can break it and get a lower degree family, which also has 2 large dimension and is still dominant. So arguing inductively, eventually we reduce to the case of low degree. And in this case, we analyze by hand, just by sort of studying the properties of the anti-canonical or the bi-anti-canonical linear series. So that's a proof of 1 implies 2. For 2 implies 3, so this condition studied by Kawakami and Nagawaka to prove that it implies this Fujita invariant, comparison. That's straightforward from their work. Finally, suppose that we have a dominant map which has larger Fujita invariant, something like this. So such maps can only exist in characteristic P, by the way. So if we have a dominant map like this, then so the first step is to classify the possibilities for this pair Y and the pullback of the canonical divisor. It turns out that the only pairs which have Fujita invariant larger than 1, there's a very short list of possibilities. So just by running the surface MMP, you can prove that either they're birationally equivalent to P2 with the hyperplane class or twice the hyperplane class. Another possibility is that it's a quadric with the restriction of a hyperplane. And the final possibility is that we have a P1 bundle equipped with a section. So our big and F divisor is a section of the P1 bundle. So now, if we have this cover where the Fujita invariant of Y is larger, by, again, some sort of MMP computation, we can construct a diagram like this. So we have S, and then by contracting -2 curves, we can replace S by its anti-canonical model. Then starting from Y, we can also contract the pre-images of these -2 curves to get some model Y prime equipped with a finite morphism. And then we can prove that Y prime is actually on our list. It's not just birational to one of these, but it's actually equal on the nose to one of these finite lists of possibilities. So once we have sort of a constrained list of possibilities for Y prime, then you just take the images of the curves under this map, and that will give you, you take some rational curves here, you take their image on S prime, and that will be a family with 2 large dimensions. Okay. Check the time. Great. Looks like we've got about 10 minutes left. So next, let me address this second pathology. So this is a pathology of dominant non-separable families. So there's a lot more of these, right? This is much less restrictive than families which have 2 large dimensions. So we would expect more possibilities. And because of that, I'm going to restrict just to considering Delpezo surfaces, no longer weak Delpezo surfaces. And I'm also going to restrict to degree at least 2. Just the Delpezos of degree 1 are a little bit too complicated. So suppose that S is a Delpezo surface of degree at least 2, then the following are equivalent. So the first is that S admits a dominant family, a dominant non-separable family of rational curves. Then it turns out that this is equivalent to saying that S is not Frobenius split. Okay. Again, you can think of this as some condition on the canonical divisor. It turns out that the condition of being Frobenius split can be phrased in terms of the top cohomology group of the canonical divisor. So again, this pathology is somehow controlled by the canonical divisor in some way. Again, there's a complete classification of the surfaces, the Delpezo surfaces of degree at least 2, satisfying these 2 pathologies. So there's 1 infinite family and 2 sporadic examples. This list is maybe short enough just to write down. So there's the cubic, there's a Fermat cubic in P3. There's that's in characteristic 2. Excuse me. In characteristic 3, another sort of example is the double cover of P2 ramified over the Klein quartic. And the final example is a class of examples. When the characteristic is 2, then we can take the double covers of P2 defined by an equation of this type. So here the key point is that we have this sort of double line, this square, as the coefficient of W. Okay, and in any case, we have some very explicit list of the surfaces with this type of pathology. Just for the sake of time, let me maybe skip this example. So I wanted to just remark that the proof is very similar. We use this special bend and break where we force our curves to go through general points, like one less than the maximal possible number of general points. And using this special bend and break, we can reduce the existence of non-separable families to low degree. And then once we reduce to low degree, we can just classify them by hand and then check that it matches the list of non-split surfaces. So this proof is a little bit unsatisfying in the sense that it doesn't give a reason why these should be related. It's just more of an observation. We classify, the surfaces of type 2 have been classified in this degree range. We classify the surfaces satisfying 1, and we note that the lists are the same. So it'd be interesting to see if there's a more sort of scientific reason why this should be true. Okay. So the last thing that we'd like to do is maybe return to the classification problem. So now let's suppose we have a Delpezo surface S, and we'd like to classify all the components of the parameter space of rational curves. So to do this, we're going to sort of rule out certain pathologies. We're not going to do it for every Delpezo surface. We'd like to sort of rule out the bad ones. So to do that, we're going to restrict the characteristic. So depending upon the degree, if the degree is at least 4, then we're going to put no restriction on the characteristic. If the degree is 2 or 3, then we're going to ask that the characteristic of our ground field be at least 3. And if the degree is 1, then we're going to ask that our characteristic be at least 11. So the degree 1 Delpezos are much harder somehow. Okay. Then here's the statement. Let S be a smooth Delpezo surface of degree D, and assume the characteristic of our ground field is at least this function we described earlier. There's also one additional case we need to rule out. If the degree is 2 and the characteristic is 3, then there's this Frobenius non-split surface, which is the double cover of P2 branched over the Klein quartic. So again, we're ruling out the pathological ones. We're not considering them. So this is an exception. We need to assume that S is not the surface. Okay. So with this setup, it turns out that the components of the moduli space of rational curves on S have the same description as before in characteristic 0, I mean. And in particular, for most Neff curve classes, there's a unique component which parameterizes birational maps onto free curves. So these weird pathologies that we see in characteristic P, they just do not occur for most Delpezo surfaces, and we can get a complete list of the rational curves which actually do exist. It looks like we're out of time, so maybe let me just point out that one of the key ideas in the proof, which I think is kind of interesting, is that it relies upon a deformation to characteristic 0. We haven't really seen this type of argument used before, so it's kind of a neat feature of the proof. Okay, let me stop there. Thank you.
Thank you very much, Brian. It was a very good talk. Okay. Do anybody has any question? Please go ahead if you do. Okay. If not, then I sort of have a generic question that about this Fujita invariant. So I mean, are the like the usual property that you that there are established properties in characteristic zero? Those things are known in positive characteristics. Let's say dimension three, because we know the MMP. Even over FP finite field, there are MMPs established now in dimension three, at least starting from characteristic five. So because I thought about this thing a long time ago, like when you have this characteristic zero and managed condition, those things that you have proved. Um, but I think, especially for example, the Christopher's that result that you talked about. I think even if I see MMP, there are some other technical difficulties. Like
That's right. Like knowing the MMP is not enough.
not enough, right? So
yeah. So for example, like one of the things that you'd like to consider is exactly this phenomenon that we were seeing, which is that sometimes like a purely inseparable map can increase the Fujita invariant. And I don't know how to try to address that using the MMP. I think that's, that kind of phenomenon is still kind of mysterious to me, in the sense that I don't have a general way of, handling the set of such maps. I don't know what to do.
Right. I think another something, just a technical thing that I noticed was that so when you consider this module, like family of curves, this either like Hilbert scheme or Chow variety, these things, and then you need to take a resolution of that one. So even though you're working in dimension three, those spaces are of high dimension, right? Okay, so you do not have a resolution of those things now.
That's right. That's a good point. Sometimes having a relative resolution is enough, but but you're right. There's lots of
what is the relative resolution?
If you have a family of surfaces or something, you can do some, it's
the generic fiber and the result of the generic fiber, the sort of the geometric generic fiber, that sort of things.
Yeah, you can try that sort of approach. I mean, sometimes that will help, but
I see. Okay, just one last thing. What was it? Okay. Oh yeah, sorry. Whenever you are saying inseparable family, do you mean the morphism that from the X to Y, that morphism is inseparable, or what do you mean exactly by inseparable family?
I mean that the by inseparable family. So if you look at the universal family over the moduli space, it has with an evaluation map. And I mean that evaluation map is non-separable. In the sense that the corresponding field extension is not a separable field extension of the generic.
Okay, thank you. Is this thing paper is already out, or are you guys?
It's on the archive.
It's on the archive. Okay, I'll take a look at that. Okay, thank you very much, Brian. Okay, yeah, I was going to attend this talk anyway, whether as a host or not. So you said okay, okay.
Thanks, everyone.
Yeah. Look, I'll wait a few more minutes. If anybody else. The relative resolution that you just talked about, right? So like even if it is what I think it is, like you go to the generic fiber and then go to the geometric generic fiber and resolve that, and then you expect that okay, you can extend it in a neighborhood of an open set of the base, something like that. Is it something like that?
Yeah. I mean, that could sometimes be. I mean, you're right that there's lots of issues. I don't know how to handle the Fujita invariant characteristics.
No, that specific thing I'm talking about is that like how do you know the geometric generic fiber is going to be reduced? I mean, it is irreducible that you can guarantee by simply assuming that roll space is normal or generically normal, and then connected fiber that will guarantee that. But why? Like, is there like a reason that you expect that is to be reduced? That is exactly precisely the separable, like inseparability of a morphism of this, which is non-finite morphism. When you say inseparable, separable, that means that as a transcendental pre-extension of the like the function field, there's supposed to be separable extensions. Like
I think you're right that you might need to do some base change or something.
Okay. Okay, you do base change first here. That you can. Okay. Okay, I see. Yes, that makes sense. Okay. Right. Yeah, after some base change. Okay. Okay. Yes. I have seen that argument before, but I forgot to reproduce it here. Okay. Yeah. After I think I attended
Oh,
that.
by the way, we're still recording, so maybe we should stop.
Oopsie. Oh, sorry.
That's okay.
Okay.